So in the previous video, we've seen goal programming problems, which we may formulate as linear programming, and then such that we may just use the ordinary simplex or maybe big M or two-phase to solve that type of goal programming. Now here we are going to look at another type of goal programming, which is called preemptive goal programming. And then you will see later that we will need a kind of modification to the simplex algorithm such that we may solve this preemptive goal programming. So let's start. In the previous video, when we talked about the deviation of variables, in that problem, the decision maker can exactly say that, for example, when we fail to meet the high income man goal, then there is a penalty of $200,000 and so on. And then also for the other goal, the decision maker can exactly say how much the penalty is. So if we have this values for each of the goal that we can't meet, which means that we can say that HIM constraint is 2 times more important than LIP. And then LIP constraint is 2 times more important than HIW. So it's good if we can exactly give the value of the penalty when we do not reach the goals. However, many times a decision maker cannot determine precisely the relative importance of the goal. So decision maker can't really say this is twice more important or 3 times more important or so on. He or she can only rank the goals without saying how many times this is more important than that. So this is the key in the preemptive goal programming problem. The key is that we can't really say exactly how much this goal is more important than that goal. We can only rank the goals. When we have n goals, we start by ranking the goals from goal 1 being the most important and goal n being the least important. Now, because we don't really have any penalty value or whatever for each of the goal, we can only use this coefficients to represent the penalty for not satisfying each of the goal. So we use P1, P2 up to Pn. We can't really say what is the value of P1, what is the value of P2. We can only say that P1 is extremely larger than P2, and P2 is definitely extremely larger than P3, and so on until the last one is Pn. Remember, we can't really define what is P1, what is P2. We can only say P1 is absolutely greater than P2 and so on. And then here, because we don't really have the penalty number, the idea is that first we try to satisfy the most important goal, which is goal 1. And then among all points or all solutions that satisfy that goal, next we are going to try to satisfy the next goal as close as possible and so on. So we keep descending from goal 1, try to satisfy goal 1 as the best that we can. And then using those solutions, try to satisfy the goal 2, and then using the solution, again, we try to solve goal 3 and so on. Now here's how the formulation look like if we use the preemptive goal programming. You can notice here that we have P1, P2, P3, and we don't really have the value of P1, P2, and P3 exactly. We only know that P1 is absolutely larger than P2, P2 is absolutely larger than P3. So what we need to do, because we do not have the number for P1, P2, P3, is that we are going to separate this into 3 z's. So here we only have 1 z. Now we're going to separate it into z1, which is the function that involves anything that is related to goal 1, and then z2 for the function that is involve everything related to goal 2, and z3 involves everything that is related to goal 3. So if we separate this, the first term is related to goal 1, the second term related to goal 2, the third one related to goal 3. So here we have this is our Z1, and then this is our Z2, this is our Z3. And then notice here that it says row 0. It means that we simply move everything to the left hand side. Okay, so here it says Z1 minus P1 S1 minus equals 0, simply because we move P1 S1 minus from right hand side to the left hand side. Okay, so those are the row zeros. So we have 3 row zeros because we have 3 goals, and then these are the constraints. And then do not forget, because we would like to have everything in standard form, for the fourth constraint we have less than or equal to, we are adding a slack variable such that now it becomes equality. So this is the formulation of the preemptive goal programming for the Priceler example. Remember that when we are dealing with Simplex, we always need to have a BFS, basic feasible solution. In this formulation, we can have the BFS with these variables. So S1 minus becomes a basic variable, S2 minus, S3 minus, and S4 minus. We may use them to become the basic variables in our BFS. However, it means that we cannot have S1 minus, S2 minus, and S3 minus in row 0. If you reviewed the Simplex algorithm, if one variable is going to be a basic variable, it can only have the coefficient 1 in just one row and then 0 in all other rows. And that form is called canonical form. Okay, so what we're going to do here is that we're going to get rid of S1 minus and then later S2 minus and S3 minus from the row 0. So how can we do this? Well, if you look at this in row 0, you have S1 minus, and then you want to get rid of it. You may use row 1, right? Because row 1 also have S1 minus. However, because this is minus P1 S1 minus, this is only S1 minus, you need to multiply the entire row 1 with P1. So P1 times 7x1, P1 times 3x2, P1 times S1 minus, P1 times S1 plus, and then do not forget also P1 times 40. Then we take the sum of these two equations. Now, when you take the sum, you get rid of this P1 S1 minus, and then here also P1 S1 minus, you get rid of them, and this is your new row 0. Notice that you do not have S1 minus anymore. And also notice that the right hand side becomes 40 P1 instead of 0 at the beginning. Do the same thing for, not the same, but very similar thing to the row 0 of goal 2 and row 0 of goal 3, such that this is the new row 0 for goal 2, this is the new row 0 for goal 3. Now here are the row zeros that we obtained from the previous slide, and then you put them in a table like this, and these are all the coefficients from the constraint. And now you can see that we now have a basic feasible solution, because here you see 1 and everything else is 0. Here it is 1, everything else is 0. This is also 1 and everything else 0. Here also this is 1 and everything else is 0. So we have a canonical form, and then the basic variables are S1 minus, S2 minus, S3 minus, and S4. So we do have an initial BFS. That's good. So you have seen in the previous slide that we have n row zeros, where n is the number of goals that we have in the problem. So if the problem has 3 goals, it means that we have 3 row zeros. So this is the first difference and also the reason why we can't use the ordinary simplex. We need to use goal programming simplex because one of the reasons is because we have n row 0. So what are the other differences? Well, in each iteration in the goal programming simplex, we need to do this. First, we find the unsatisfied goal with the highest priority. We call this goal as goal I prime. And then in the row 0 that is related to goal I prime, we try to find a variable that is the most positive, that has the most positive coefficient, because the problem is minimization. So we find the variable with the most positive coefficient, but then there is a requirement. We need to find the most positive coefficients whose coefficients are not negative in the higher priority goals. So we need to check in the goals that is higher than I prime whether this variable has negative coefficient or not. If it has a negative coefficient in the higher goals, then it means we cannot pick this variable and try to find the next most positive coefficient and so on. If we find such coefficient, then we just perform arrow or elementary row operations and then repeat this step. Again, we try to find the variable that is the most positive in goal I prime. Suppose we cannot find any variable that satisfy this requirement in goal I prime. It means that we need to go to the next lower priority goal, which is goal I prime plus 1. And then we repeat the second steps again, try to find a variable that is the most positive in that row with the requirements that the coefficients of that variable in the higher priority goals cannot be negative. So we keep repeating this. And then in each iteration, when we perform arrow or elementary row operations, we need to update all row 0. So we really do or perform the arrow for all rows that we have in the table. And finally, the goal programming simplex will reach the optimality if all goals are satisfied, which means that Z1 equals Z2 equals Z3 up to Zn equals 0. Now let's apply the goal programming simplex to the initial table of the Priceler example that we have. So the first step is we're going to look at the goal with the highest priority that is still unsatisfied. So in this example, the highest priority is HIM and it is still unsatisfied. The reason is because the Priceler example is a minimization problem, and then we see that here we still have positive coefficients. So 7p1 and 3p1, there are positive coefficients. In the case of minimization, if we still have positive coefficients, we have not reached the optimality. So we are going to ignore the lower priority goals and just focus on this goal. So here we pick the one with the most positive coefficients, so 7p1, and this will become the entering variable. As usual, we are performing ratio test, right-hand side divided by the coefficient in this column, right-hand side divided by the coefficient again, and so on until we get this ratio test results. Pick one, always pick the lowest ratio test result. It means that because this is the lowest, 40/7, it means that at this position in the next table, we must have the value of 1 in that position and 0 in the other position in this column. So we perform arrow or elementary row operations until we get what we want for this column. Now when we look at this row 0 of HIM, we see that we do not have any positive coefficient anymore, which means that we have satisfied this goal. We can also see that we have reached the optimality for row 0 HIM because the Z1 value equals 0. Remember that the penalty for HIM is only happening when we are underachieving the HIM goal. Here you can also see that S1 minus is a non-basic variable, so it means S1 minus equals 0. We are not underachieving the HIM goal. such that, in other words, we are already satisfying this goal. We have satisfied the goal for HIM, so we are going to look at the second highest goal with the second highest priority goal, which is LIP. So we are just looking at LIP, and then again, because this is the minimization case, we still have positive coefficient here, which means that this goal is not satisfied yet. We pick the most positive one to become the entering variable. We perform ratio test, and then the smallest ratio test is obtained at this row. So at this position, we must perform error such that in the next table it will become 1. So we perform error, and then that position becomes 1, and all other values become 0 in this column. Okay. Now you can see that Z2 is already 0 as well, which means that we already satisfied LIP goal. Now when we move to the third goal, HIW, we see that we still have a positive coefficient. So this goal is not satisfied yet. However, before you decide to make this x2 becomes entering variable, you need to check the higher priority goal. So here you check that actually in the higher priority goal, it has a negative coefficient. Whenever it has a negative coefficient in the higher priority goals, you cannot pick this variable to become entering variable. Again, you need to check the higher priority goal, and then all the higher priority goals. If any of them has a negative coefficient, means you cannot pick this variable as an entering variable. Now, if we try to find another variable that is also positive in this row, for row 0 HIW, we do not find any other variable with positive coefficient, which means that we cannot do anything for this table anymore. Which means that we have reached a point where we need to stop, although this solution is not optimal because Z3 is not 0 yet. It is still equals to 5P3. And you can also see that this result happens because this value is with respect to the column S3 minus, and S3 minus means that we are still under the goal for HIW. We have not achieved the goal to reach high income women. We are still under the goal by 5 million. That's why the Z3 is not 0, but we cannot do anything farther, because when we do something to the solution, it will disturb the higher priority goals, and we do not want to do that. We never want to disturb the higher priority goals. Now this table simply shows that when we have different order of the priorities, we will have different optimal solutions, which means that the number of ads that we purchase will be different, and the number of deviations may be different as well. So this is the one that is the one that we have in the example. So the priority is HIM, LIP, and HIW. But you can see that if we have different ordering, then the solution may be different as well. Okay, so to summarize the goal programming topic, first, if you or the decision maker can exactly define or tell the amount of penalty when we deviate from the goals, you can just use, for example, the objective is to minimize the sum of the penalty of the deviations. And then you just solve the problem using Simplex, Big M, or two-phase as usual. However, if the decision maker cannot exactly tell the amount of the penalty, he or she can only say this is more important than that, this has a higher priority than that, then you need to formulate the problem as preemptive goal programming. And as the consequence, you need to use goal programming Simplex to solve the problem. There are some differences, and then one of them is whenever you try to decide which variable becomes entering variable, you need to check the coefficients of that variable in the row 0 of the higher priority goals. The idea is we do not want to disturb the optimality that we have achieved for the higher goals when we are solving the row 0 for the lower priority goal. So that's the end for the goal programming topic. And next week we are going to look at something really new, which is called sensitivity analysis. So see you on the next week, and thank you.